everyone, my name is Jie Ying, who is taking the biomaterial science class.
Today, I would like to talk about the topic of contextual control of adipose-derived stem cell function, implications for engineered tumor models. The keywords for this article is adipose-derived stem cells, tumor stroma interactions, myofibroblast differentiation, tissue engineering, and biomanufactured tumor models. This review discusses the plasticity of adipose-derived stem cells (ASCs) in the tumor microenvironment, as well as other disease contexts such as obesity and aging. Also, this article highlights some advanced biomanufacturing technologies that could be used to integrate stromal parameters into the next generation of engineered 3D tumor models, and such models will enable new insights into ASC-dependent microenvironmental aspects, contributing to tumor initiation and progression that may ultimately be targeted for improved anti-cancer therapies. Adipose-derived stem cells (ASCs) are multipotent and thus an attractive cell source for tissue engineering and regenerative medicine. Nowadays, tissue-engineered 3D culture models are increasingly utilized to study tumor cells in the context of enhanced biological complexity and have contributed to an improved understanding of cancer. First of all, ASC, as shown in Figure 1, display a high degree of plasticity. Stem cell plasticity is the ability of stem cells to give rise to cell types formerly considered outside their normal repertoire of differentiation for the location where they are found. As shown in Figure 1, ASCs are able to differentiate into, for example, adipose, endothelial, and many other lineages. However, when ASCs are exposed to aberrant microenvironmental conditions that are caused by cancer, obesity, and aging, these cells differentiate into tumor-promoting myofibroblasts that in turn promoted tumor regenesis by promoting fibrosis, inflammation, and consequential changes of cell extracellular matrix physiochemical properties such as composition, structure, and mechanics. Next, here are some biomanufactured tumor models. For A, multiparametric star PG heparin composite hydrogels permit studying heterotypic interactions between tumor cells and endothelial cells, and MSCs as a function of ECM composition, degradation, growth factor binding, and mechanical properties. For B, synthetic fibrous materials can extract changes in cellular behavior in response to ECM bulk versus individual fiber mechanical properties. For C, interpenetrating networks of basement membrane and alginate allow for independent modulation of ligand density and ECM stiffness and analysis of the resulting consequences on tumor cell invasion. For D, PEG hydrogels with phototunable stiffness facilitate studies to examine the effect of temporal dynamics of ECM remodeling on tumor regenesis. After that, here are some examples of biomanufacturing strategies to integrate vascular structures into 3D culture models. For A, soft lithography-based fabrication of collagen-embedded microvessels. B is the microfluidic-based vascular systems, C is the complex 3D printed vascular networks, and D is the 3D bioprinting of cell-laden inks. So, the conclusion for this research article is that exploring biomanufacturing approaches toward the development of advanced 3D in vitro models of the tumor microenvironment will not only advance basic research of cancer, but will also improve the safety and predictability of clinical ASC applications. Also, future work conducted at the interface of tissue-engineered tumor models, biomanufacturing, and the stem cell field will allow the discovery of new targets to improve cancer therapy and advance clinical solutions for tissue regeneration. That's all for my presentation today. Thank you.